This second tutorial explains how to create shaders and work with buffer objects in OpenGL. All the includes and libraries files remain the same as in tutorial 1, but we now need to add an additional C++ file, which can be used as a header file if you wish, and two GLSL shader text files, which are the Vertex shader and the Fragment shader. Go ahead and add the three shader files as I'm demonstrating here. For the shader configure file, you'll need to add a new item, whereas I'm adding an existing item simply because I already have the file ready. However, I'll show you how to add a new file for both the Vertex shader and the Fragment shader, because it requires you to first create a new text file and then change the text file's extension to either .vert or .frag. As always, you can find all the source files on programmingcreatively.com to save you having to type it all in. There are two additional includes that need adding. fstream, which stands for file stream, which is used within shader configure to read our Vertex shader and Fragment shader text files into memory. The first part of the program up to and including section 2, glad, load OpenGL function pointers, is exactly the same as already explained in tutorial 1, which covers how to download and configure various software, and then how to create an OpenGL context window by using glfw. Now let's examine the C++ code of our shader configure header file, which is called whenever we need to create a new program object along with their accompanying shaders, which in this instance is our Vertex shader and our Fragment shader. In the constructor, we receive pointers to the string literals that represent the directory path and file names of our two shaders. We use input file stream to open and read the shader text files, and we use strings to contain the contents of those files as they're being read. For each shader, one character at a time is added to the string variable until the entire file has been read, and then the input file stream is closed. After the text files have been read, they can be outputted to the console window via character output, also known as cout. This allows us to confirm the content of our shader file's existence as stored within the string variables. Any error messages will also be displayed in the console window. We then access each string object by calling cstring, which returns a pointer to the address of where each shader file is stored as a character array. Then we assign that address to a constant char pointer variable. Next, it takes only 3 OpenGL function calls to create and compile a shader. glCreateShader creates an empty shader object and returns an unsigned integer which is used as a handle to refer to the newly created shader. By passing our pointer variable and shader handle to glShaderSource, OpenGL can then associate the shader array object with the handle, and then to compile the shader, we simply pass our shader's handle to glCompileShader. The next 3 OpenGL function calls create our program object and attach both the Vertex shader and Fragment shader to the newly created program ID. The program object is all of the shader object files that we've created, 2 in this case, combined together into one entity which contains all of the individual shader stages being used. By passing the program ID to glLinkProgram, our 2 already associated shader object files become linked together and compiled to become this one program object. The program object itself is executable code, which we bind to the OpenGL context to use as part of the current rendering state by calling glUseProgram, and typically unbind at any point in the main loop where another shader program needs to be bound instead. The remaining OpenGL function calls are all for shader compilation and program link error checking. There are 2 specific functions used to check the individual shader compile status and 2 specific functions for checking the link status. OpenGL has 3 different types of triangle primitives, but we're just going to use GL triangles. To produce a square we need 2 triangles, and each triangle consists of 3 vertices, which is 6 in total. We're not yet working in 3D, therefore OpenGL's normalized device coordinates, also known as NDC space, which range from -1 to +1 for all 3 axes, x, y and z, are the values that we need to use for drawing at this stage. Therefore, by using values ranging from -1 to +1 for all of our 18 vertices, it means that all of the initial window size area will be perfectly filled, regardless of the aspect ratio of the window's width and height, which was set when we called glfwCreateWindow. Alternatively, we can use glViewport to control the effective display area. To do this, we can pass the frame buffer size in pixels to glViewport. Note that the frame buffer size is sometimes the same as the screen size in pixels, but not always. When we compile and run the program, we can see the rectangle through the triangle because the triangle overlaps the rectangle and is drawn in front of it. Creating vertex array objects, vertex buffer objects, and defining their vertex data all need to become associated with one another in the correct order. After creating the buffer objects, the VAO is bound first, then the VBO is bound and initialized, and then finally the data is defined as a vertex attribute array. We'll now examine more closely just two of the following OpenGL function calls that each require several arguments. When calling GL buffer data, we need to let it know four things: the type of buffer target, the total size of the vertex data in bytes, the address where the data is stored, and how the data is going to be used. First, we tell OpenGL which type of buffer object is being used. We then use the size of operator to get the total data size of our vertices. Then we pass in the array which provides the address as a pointer, and then finally we pass glStaticDraw, which tells OpenGL that the data will be modified only once and used many times. When calling glVertex attribute pointer, we need to let it know six things: the attribute location index within the vertex shader, the number of components per vertex, which is 3, the type of each component, which is float, that we don't want the values normalizing, the stride, which means how far along inside the buffer in bytes until the next set of 3 components will arrive, and then the final parameter is a void pointer that exists for legacy reasons, which can be set to 0. Within the main loop there are only 3 new OpenGL function calls. glBindVertexArray tells OpenGL which vertex array object to use. glDrawArrays needs to know 3 things: that we're rendering triangle primitives, that we want to start drawing from the beginning of our vertex array data, and then finally the number of indices in our vertex array, which is 18 indices for the rectangle plus 9 indices for the triangle, which totals 27 indices. To calculate the size of the array, we divide the total array size in bytes by the size in bytes of just one of the entries in the array. We then call glBindVertexArray once again to unbind our vertex array object, which, as commented in the program, isn't really necessary in this simple case of using only one VAO. The first line in the vertex shader states the version of OpenGL being used. Layout location equals 0 is our input attribute vertex data that we've already defined on the CPU side. The next 2 lines within our main function declare one variable each, which are both based on the attribute position. The first one, being of type flat_out_vector2, is used to pass APOS values to the fragment shader such that they won't be interpolated by the fragment shader. In contrast, the second line, outVector2, is used to pass those same values, but this time they will be interpolated by the fragment shader. The first part of our fragment shader is equivalent to the first part of our vertex shader, in that it receives the values that the vertex shader is sending. Within the main function, for the rectangle, the red and green colour values are represented by the vertex X and Y position values. Blue is fixed at 0.5 and the transparency value is 1, which means 100% opaque. For the triangle, it's the green and blue colour values that are represented by the X and Y position values. Red is fixed at 0.5 and the transparency value is 0.45, which means 45% opaque. The triangle's vertex position data is distinguished from the rectangle's vertex data by the if statement, by checking that each vertex's X position value is equal to 0.75, which enables us to treat the triangle differently to the rectangle. Now let's run the program with the transparency value first set to 0.45. Now as a comparison, let's reduce it to 0.15, which, as you can see, makes the triangle appear very faint. If we then increase the value to 0.85, the opposite happens, in that only a small amount of the rectangle's pixel colour is added to the triangle. Finally, let's set the red, green and blue colour values to a pale orange colour, instead of using the interpolated vertex position values.